if you'd like to introduce.
Certainly. Let's see. I suppose I should wait until the YouTube started. Okay, time delay. In that case, hello everyone and welcome to the Cambridge University Physics Society. Today we have Professor Chris Reynolds here to talk about how to measure the spin of a black hole. Professor Reynolds did both his undergraduate and PhD here at the University of Cambridge. After his PhD, he became a research associate at the University of Colorado, and later he was appointed a professor at the University of Maryland. He is the current Plumian Professor of Astronomy at Cambridge University and a successor to such renowned scientists as Sir Arthur Eddington and Lord Martin Rees. Much of his work, and that by his group, centres on the astrophysics of black holes and the role they play in the universe, addressing four specific themes: observational probes of relativistic physics close to black holes as probes of physics beyond the standard model, theoretical studies of accretion disks, and theoretical studies of the influence that supermassive black holes have on galactic scale structure formation. Before we begin, I'd like to take a moment to thank our sponsors: Seamless, Riverlane, TTP, TPP, Define, Jane Street, and CGG. Please post questions either in YouTube or Timeout chat. With all that said, I hope you enjoy the talk, and I hope to learn much about how to measure the spin of black holes. Thank you very much. Chris?
Thank you very much, Will, and thank you for the invitation to be here. It's a great pleasure to come and speak to the Cambridge University Physics Society. Many years ago, I was a member of this society, and I enjoyed many talks. So it's a great honour to be here, giving you a talk. So today I'm going to talk about one particular aspect of my work, how to measure the spin of a black hole. This is the outline of what I'll be addressing. So I'll just quickly run through the basics of what is a black hole, what are the key characteristics of a black hole. But then, of course, I want to motivate the question of why is the spin of a black hole particularly important. So I'll spend a little bit of time on motivating that question, and then I'll get into the question of how do we actually go and measure the spin of a black hole. And I'll focus on a couple of topics and show you actual data and actual results. One is looking at accreting black holes and telling you what you can do with X-ray astronomy, so X-ray observations. And then the other one is looking at binary black holes with gravitational wave observations. And as I said, I'll show you actual results and implications, and sort of tell you where some of the current thinking and current research is in this topic. I think, as Will mentioned, if you have any questions, just put them on the chat, and I believe that we'll read them out, and I'll try to address them. If you have any longer questions, we can talk about it at the end. Okay, so the very basics of what is a black hole. Most of you have probably come across this concept of a black hole before. But basically, a black hole is the complete victory of gravity over all other forces. So we imagine that we have some lump of matter that has undergone a complete collapse, where gravitational forces have just crushed it down to ostensibly a point. And we'll talk later on about exactly what matter we're talking about, how's this kind of process happen. But for now, just think you've got some lump of matter that has undergone a complete collapse due to its own gravity. And what we end up with is a place where at the very center, we basically violate the laws of physics as we know. So oops, that shouldn't have appeared. But then that's surrounded by what we call an event horizon. So the event horizon is essentially the boundary where the escape velocity from this object is the speed of light. So outside of here, light can get out to us. Light can we can receive signals from outside of here. But inside of this radius, gravity is so strong that it's pulling everything, even light, inwards towards the singularity. One important characteristic of the event horizon here is that if we are looking at objects that are getting close to a black hole, it appears that time starts to run slowly as you get towards that event horizon. And for a non-rotating black hole, it's quite easy to actually calculate the formula for how that works, and you get something like this. So, if you imagine you have a clock ticking with a rate, a gap between the ticks of delta t, and you put that clock near a black hole, and sort of hover it somewhere near the black hole, and you ask how long do we see the ticks to be, and they're delta t primed, then this is a formula that gives you the length of those ticks. And this can become quite a small number as the radius approaches 2 gm over c squared, and then we raise that to the power of -1/2. So as we get closer and closer to the black hole, the ticks that we see take longer and longer and longer. And as you get right up to the event horizon, which is at r equals 2 gm over c squared, then we'll see this clock freeze. So now one important thing to recognize is that this event horizon that we talk about is in some sense not a real thing. If we were flying into the black hole, we would actually pass through the event horizon without realizing it. And one good way to think about the black holes, there's actually quite a close analogy you can make with flowing fluid. So you can actually make this analogy fairly mathematically rigorous, where you imagine that you have water flowing across into some precipice, and you can imagine that if you were in a rowboat here that could only go at a certain speed, let's call that speed c. If you're in a rowboat here, then if you're a long way from this precipice, you could easily row away. Whereas once you get close enough to it, the flow speed will start to become equal to or greater than the speed you can row your boat. And once you're inside that radius, no matter how fast you row, you'll be dragged inwards. And that's actually a pretty good analogy with the black hole. So the event horizon, which here would correspond to the rim of this precipice, is not a place where physics is really going crazy. It's not a singularity, even though it appears that time freezes there for outside observers. It really is. So in some sense, we call it a coordinate singularity. You can actually remove this if we go to a different coordinate system. Now, what if instead of this kind of object, we have this? So there's actually a vortex of water going down. This is actually a pretty good model for what happens when you start to give the black hole some angular momentum. So if you give the black hole angular momentum, then in some sense the space-time around the black hole is actually set into rotation, and this has a whole host of consequences. So one of the most important ones is that there is a region surrounding a rotating black hole that is, we call it the ergosphere for reasons I'll say in a minute. And this is a region where this dragging effect of space, we call it frame dragging. It's the dragging, it's the sort of induced rotation of space-time due to angular momentum that the black hole might have. It gets stronger and stronger as you go towards the black hole. And there comes a point when, in fact, it's impossible to stand still. So there comes a point when, coming back here, if you can, again, row at a certain speed, there comes a point when the rotation of the space-time around the black hole actually becomes faster than the speed you can row. So in other words, here, inside this region here, the rotation of the space-time, if you like, is actually superluminal. It's actually going faster than c. What happens in this region is it means it's impossible to stand still. To stand still, you'd have to be sort of relative to the local space. You'd have to be going faster than the speed of light. And what this has other consequences. Means, for example, if you were to fire in a photon towards this rotating black hole, then the black hole is rotating around like this. Can you see the pointer, by the way? Just
yes.
Good. Just want to make sure that you know what I'm referring to when I say this. So when the black hole is rotating around like this, you send a photon in, then the photon, as it falls in, actually starts to go into rotation around the black hole. If you send a photon in going the opposite way, then for a while it's falling in towards the black hole and sort of orbiting around the opposite direction. But once it hits the edge of this region, this ergosphere, it gets whipped around and has to go in the same sense as the black hole when it falls in. So this is the ergosphere. So why is this spin important? Well, the spin of a black hole is actually one of the fundamental properties that defines a black hole. There's something called the no-hair theorem for black holes, which states that any isolated black hole is described by just three numbers, three quantities: mass, spin, and charge. And if you ask, well, why those three? Those are the three fundamental conserved quantities of classical physics. If you're forming some object from some mass, then you have to conserve mass energy, you have to conserve angular momentum, that's the spin, and you have to conserve its electrical charge. So those are the three fundamental quantities of classical physics. And realistically, if the black hole did have some very, very appreciable charge to it, suppose it had some enormously strong electrical charge, what would actually happen is it would start to pull in opposite charges from the surrounding plasma, from the surrounding gas, and it would discharge. Basically, be a lightning storm, it would discharge. So realistically, any black hole, any astrophysical black hole, any black hole we're going to find out there, is defined by just two numbers, mass and spin. So the first reason why spin is important is that it's one of the two quantities that's basically going to define your black hole. The second reason why spin is important is that, as an astronomer, I care not just about the physics of black holes, I care about how they actually got there. What kind of astrophysical processes, what kind of astronomical processes led to the black hole actually getting there. And so spin is actually a fossil record of how that happened. The spin of a black hole, or the angular momentum of the black hole, is just the sum of all the angular momentum that went in to make the black hole. So as we'll see later, different formation scenarios for black holes predict different spins. So to measure the spin, we can say something about how the black hole got there. And then the final thing, final reason why spin is important is that spin is actually a very important energy source in astronomy. The rotational energy of a black hole can actually be tapped through various processes, and it can actually be very high. So let's put some numbers to this, or some mathematics to this. If the angular momentum of the black hole is J, I'm going to define something called the dimensionless spin parameter, which is this A quantity here, which is simply taking J and putting in enough powers of C, G, and the mass of the black hole to make it complete, to make it a dimensionless number. Okay, so this is my dimensionless spin parameter. So if A is 0, the black hole is not spinning at all. And it turns out that the maximum that this A can be is 1. Beyond that, in fact, the general relativity tells you that it will not be a black hole any longer. There won't be an event horizon. So just in our first sort of use of this quantity A, we can actually figure out what the energy associated with the spin of a black hole is, a black hole of mass m, if it has a spin parameter A, and you get a formula that looks like this, kind of slightly cumbersome formula, but so if you do have a maximally spinning black hole, so an A of 1, that's as fast as a black hole can spin. If you put that in there, you'll get 1 minus 1 over the square root of 2 is what you get, times mc squared. That's 29% of mc squared will be the rotational energy of the black hole. So almost 30% of the rest spin energy that in principle can be tapped and drive astrophysical phenomena. And the classic phenomena we talk about when we think about spin as an energy source are jets. So in many systems where we believe there's a black hole, so this is a nearby galaxy called Centaurus A, we believe it's got a massive black hole at the center, and the colored images here, this is a radio map, and you see jets that are streaming out of the center of this galaxy, powering these huge lobes that exist on each side of the galaxy. those jets extend all the way into the very, very center, and we believe that it's plasma that's being shot out of the center at very great speed, 95% the speed of light or more, and is tremendously energetic. So there's a lot of energy being pumped outwards from the black hole. We believe the energy source for these kind of jets is actually black hole spin. And just to briefly give you a cartoon of how that might work, and what we actually believe is going on is that down at the center here, we have a black hole. We have a disk of gas surrounding it. This is an accretion disk that I'll talk about more a bit later. And then threading the black hole is a magnetic field. And it has been shown in the 1970s by Roger Blanford and Roman Znajdek that if you have a magnetic field threading a black hole, and that black hole is spinning, then what you do is you coil the field up, and you can basically send out you send out energy out down magnetic coils, and that energy is coming from the spin of the black hole. So this is the way that you can tap the spin of the black hole, and you can drive magnetic jets out of the center of the system. Okay, so that's all motivation for why spin is an important quantity to look at. So let's actually now think about how we can go about measuring it. And let me start off by saying, let's start thinking about isolated black holes. And I'm going to draw a distinction between isolated black holes and binary black holes. So when I mean isolated, I don't mean they're completely isolated from everything. I mean they're not near another black hole. So isolated black holes are, of course, if they truly are isolated all by themselves, they're incredibly difficult to see or detect or measure because they're black. We do see them, however, when they have matter that is accreting into them. And we believe that they're everywhere. So, in almost every galaxy that we know of, we believe has a supermassive black hole, most times a single supermassive black hole at the very center. So this is one particular galaxy that many of us worked on. It's called NGC 1365. And if I take this is slightly done for artistic drama, but if I take this figure and I drop on it an image from an X-ray telescope, so this is from an optical telescope, but if I drop on an image from an X-ray telescope, you see this. There's a very powerful source of X-rays from the very core of this galaxy, and this is believed to be coming from material that is accreting onto this central supermassive black hole. I won't talk about this very much, but just to say, it's not just a powerful source of X-rays; it's a highly variable source of X-rays. So this is what we call an X-ray light curve from another one of these examples of an accreting supermassive black hole. And this is the count rate we're seeing in our detector, so counts per second in our X-ray detector, versus time. And to put this time coordinate into context, 1 day is about 86,000 seconds. So 1 day is, some point around here. So this whole light curve is only a day and a bit long, and you can see that there's tremendously rapid flaring and variability during this time. So this accretion process is a very interesting, unsteady process. So and the other aspect about accretion is that so much of my work is on these physics of these accretion disks. Fundamentally, what's going on is you're feeding matter inwards, matter's spiraling inwards towards the black hole, and you're converting its gravitational potential energy into other forms of energy. It's coming out as electromagnetic radiation, such as the X-rays that I just showed you. It also can come out as kinetic energy of the jet, which is on this cartoon. It can come out as kinetic energy of a wind that gets kind of blown off the disk through various processes. But the other thing is that it's an extremely efficient process. So if you take 1 kilogram of matter and you drop it into a black hole, it releases about 200 megaton TNT equivalent of energy. That's about 10% of its rest mass energy. That's 10 times more efficient than the thermonuclear fusion that happens in the sun. So it's an incredibly efficient way of taking matter and turning it into energy when we drop it into a black hole. Okay, back to spin. If we want to measure the spin of a black hole, of one of these black holes, what we have to do is to characterize the effect of the black hole spin on this accretion disk, and then figure out how that affects the observables, how that affects the actually aspects of the accretion disk we can look at. And an important thing here, we can sort of go back to the basics of black holes, and this is the kind of thing that is bread and butter if you take a sort of black hole course in like part 2 or part 3. There are various special radii that exist around a black hole. So here's a cartoon. Here's our black hole. The event horizon is the edge of this black disk, and it turns out that there's a very particular radius called the photon circular orbit, where light can orbit in a circle. So there's a special radius where a photon will actually orbit around in a circle. Outside of here, the photon would just fly off. Whoops, sorry. Inside of here, the photon would actually fall into the black hole. But that's the photon circular orbit. And it turns out, you've got a glimpse of this just now, but the photon circular orbit is what you are actually looking at when last year there was this famous picture of a black hole that was announced. And of course, there's actually 2 black holes on this front page. There's Brexit, and then there's also the black hole in M87. So what you're actually looking at here in this image from the Event Horizon Telescope that made a lot of newspapers last year is actually this photon circular orbit. This is the data from the Event Horizon Telescope. If we look at the model that we believe fits that, this is a theoretical model that we believe is the sort of defuzzed image of this data, then this ring that is being picked out in the Event Horizon Telescope is actually this ring here, we believe, which is radio emission that is orbiting around the black hole in this innermost stable circular, in this photon circular orbit. So that's what we're looking at there. And just to briefly say, the kind of way you make these kind of images is you can have a lot of fun with this by having a code that can do ray tracing through the black hole space-time. All kinds of funky paths that photons can take around the black hole, including being wrapped up by the black hole spin. Okay, so back to our special orbit. So that's the photon circular orbit. Outside of that is something called the marginally bound orbit, which is a slightly technical thing, but if a particle is on a circular orbit at this location, it actually has the same total energy as if it was at rest out at infinity. So you can actually take a particle at rest from infinity, put it here, and you've made no change to its energy. So that's a slightly technical thing, but it turns out that is important in accretion disk models. But a particularly important one then is further out. There's something called the innermost stable circular orbit. So what does this mean? Outside of here, if you have a particle that's in orbit around the black hole, it's pretty much like the kind of orbits you're used to from studying, planetary motions around the sun. If you have something in orbit around the black hole and it's in a circular orbit, but then you nudge that circular orbit, the orbit is stable, okay? Or it just goes slightly elliptical and nothing happens. Around a black hole, that remains true down to a particular radius. And I've done it to scale here, so that radius is 3 times the event horizon. Inside of that radius, it'll just fall into the black hole. So that's called so that's why this is called the innermost stable circular orbit, or sometimes just called the ISCO. Now the critical thing is that each of these 3 orbits is just you can derive it for using from the basic equations of general relativity for these black holes. So it's relatively well defined and straightforward to derive these radii. And it turns out each of these radii depends upon the rotation of the black hole. And we can graph that out So it turns out that, and this is our dimension of the spin parameter again, so non-rotating black holes are 0. A dimension of the spin parameter of 1 is a black hole that's spinning maximally. And in this sense, +1 means that this is with respect to prograde spin, so spin in the same direction as our particle is orbiting around. And then -1 is retrograde spin, so spin that's the opposite direction to the particle orbit. And we find that each one of these orbits is actually a function of the spin. So the innermost stable circular orbit, which will turn out to be a particularly important one, for
Hello, Chris. We
yes.
happen to have a question from YouTube from Jingming C. What happens to a photon when it enters the black? When it enters the black hole, does it get converted into energy?
Excellent question. So when the photon enters into the black hole, so from the point of view of the photon, what would happen is it would actually pass into the black hole, it would carry on going, and eventually it would strike the space-time singularity. Then actually we don't know what happens to it, but globally we know its energy adds on to the rest mass energy of the black hole. So if a black hole is accreting photons, that ultimately just adds into the rest mass energy of the black hole will grow. Its overall mass will grow. So that's a good question. Thank you.
Okay. Also a further question from Jingming.
Yeah.
Can you elaborate more on the marginally bound orbit? Why does the energy of an object not change?
That's it. Let me go back. This is the good question. So, if you imagine a particle that's in a circular orbit, and you gradually bring it closer and closer in, then you actually, that particle have to lose energy to fall in. It's just like a satellite that's orbiting around. As it loses energy, it falls inwards. So as a particle from infinity starts to fall inwards, it loses energy. That is true up to the point where you're in the most stable circular orbit. And it turns out that if you can somehow force the particle to stay on a circular orbit, which is a somewhat unnatural thing to do because it's unstable at this point, but if you can, inside of this, if you can force it to stay on a circular orbit and you can keep it moving inwards, it actually has to increase its energy again. You now get sort of a potential barrier you're climbing back up, essentially because the particle is having to go much faster than normally you'd think it would have to, just to resist the gravitational field of the growing gravitational field of the black hole. So you have to actually add energy in to make a particle go in a circular orbit as you pass in. And by the time you get to this marginally bound orbit, you've added in as much energy as you've lost falling in from infinity to this point here. So that's why this marginally bound orbit is this special place where you've got the same energy here as you did at infinity. Now you can carry on, if you keep it on your circular orbit, you can carry on all the way down to the photon circular orbit. Again, you have to continually add energy to keep it on those orbits. And strictly now, if you imagine you've got a particle, the only way to be on the photon circular orbit is for that particle to be going at the speed of light, which of course would mean you'd have to give it, formally an infinite energy. So it's an interesting behavior in terms of the energy a particle would have as it's accreting in. Yeah, that's a good question, Jimmy.
Also, one more question from YouTube. I hate to keep interrupting with this. From Instinct 7, can we see behind the black hole because of the curvability of light?
Yes, we can. Let me. Can we see it? Can we see it here? To some degree, sorry, I lost my pointer. To some degree, that's sort of what we're seeing here. So, in this computer animation of a model accretion disk, much of this emission we're seeing here is actually sort of behind the black hole. It's being kind of lensed around. So even though it looks like the horizon is here, it is here, but much of this emission here is actually from behind. So you're not getting a flat image here of the disk. You're getting a very distorted image with much of this emission actually being behind the black hole. That's a good question. And again, you can sort of see that from this, well, maybe from this animation, that if we imagine that we are up here somewhere and these are light rays, some of those light rays can come to us from what would normally be considered behind the black hole. So, yeah. Good. Yeah, good questions. Any other questions, Will, at this point, or
that would be it for now. I think I'll wait till ask yours at the end because we're around the 30 minutes mark now. So I thought it'd be good to.
Great. Yeah, good. That's roughly what I expected. Yeah, good. Right. So, innermost stable circular orbit is a function of spin. So why is this important? Because it's important because the innermost stable circular orbit is actually a big deal when it comes to the structure of the accretion disk. And here's a cartoon showing that. If you have the accretion disk that's which of course is just material that's largely orbiting the black hole with a small in-spiral, once it gets the innermost stable circular orbit, that is actually a natural place for it to stop orbiting around and to start spiraling in very quickly. So in many accretion disk models, and of course there's no such thing as one accretion disk model, this is still a work in progress, there's hundreds of people working in accretion disk, but in many accretion disk models, the innermost stable circular orbit, the ISCO, is a sort of natural inner edge to the accretion disk, or at least to many aspects of the accretion disk. So if we could measure something in the observables that tell us where that edge is, then we've got handle on measuring spin. And just to show you this, not in a cartoon, but in an actual computer simulation of an accretion disk, this is from one of my PhD students, or former PhD students, Drew Hogg. This is a simulation of a magnetically turbulent accretion disk, or a sector of one around a black hole. And this inner edge you see here is where the density is plummeting off because you've reached this inner edge. There is still gas in here, it's just very low density. So this edge really does seem to be defined by the innermost stable circular orbit. So let me show you, let's just quickly jump to some data. At first you'll look at this, not know what you're seeing, but I'll walk you through it. So this is an X-ray spectrum of one of these supermassive black holes in the core of a galaxy. And this is from taking data from 2 X-ray observatories. Of course, X-ray observatories have to be in space because the Earth's atmosphere absorbs X-rays. So these are actually in satellites. So the black red data are from something called the XMM Newton satellite, which is a European satellite, and the green and blue is from something called the New Star satellite, which is a NASA satellite. So this is the X-ray spectrum of it. Now, it's quite a complicated spectrum. It's shaped by lots of absorption and emission processes that I'm not going to get into. But if we model a lot of the less interesting stuff, the absorption, what we end up with is a spectrum like this. And I want to highlight this thing here. This is an emission line. And we know what this emission line is. It's iron. This is just the fluorescence of iron. If you take a lump of iron, shine X-rays on it, you'll get an emission line at this energy, 6.4 keV. So what's happening here is that we have an X-ray source here. We generically call it the corona. We don't really know what the physics of it is, but we have an X-ray source that's giving us a powerful source of X-rays. And those X-rays are shining down on the accretion disk. And the accretion disk, there's some small fraction of the atoms in this. Most of the atoms in this are hydrogen and helium. Some small fraction of those atoms are iron atoms, and that iron is just fluorescing in this line. But you see, this line is not a sharp line. It's a line kind of with a triangular base to it. That triangular base is from strong Doppler shifts and gravitational redshifts that can tell us the line that can tell us where the innermost stable circular orbit is. So let's see, I guess I'll go through this quickly. So imagine, actually no, I'm not going to go through. I'm going to skip to this. So this is that line profile, sort of in a model form that I showed you. And what you've got here, again, just to reiterate, is you have an emission line that's really just a sharp emission line, but then you are looking at it from a point of view of a disk that's rotating around. So the line is broadened by Doppler shifts. I will actually show some of this. The line is broadened by Doppler shifts, and then it's gravitationally redshifted. So just to walk you through this, if you imagine you have some annulus of the disk that's a long way out, then you get a blue shift and a red shift if we're looking at the disk not exactly face on, and you'll get a blue shifted peak of the line and a red shifted peak of the line like this. So the line will be broadened a little bit. If you look at a ring of the disk that's closer in, say 100 gravitational radii, this is a particular measure, so 1 Rg is gm over c squared, then the line will be more strongly broadened, and we see an asymmetry in the line here. And this asymmetry is largely because the blue shifted part of the line, which is coming from material that's coming towards you, there's special relativistic aberration, which means that emission is beamed towards you. If we come in even closer to 30 gravitational radii, this effect gets stronger. You start to see that the whole line centroid is shifted inwards. And that shifting inwards is largely due to gravitational redshifting. It's the fact that clocks are running slowly as you're getting close to the black hole. And this effect just gets stronger and stronger as you go closer in. But of course, we can't resolve the disk. We don't see individual radii. We see the whole disk added up together. And so that's why the line has this triangular shape. So if we sort of skip back to where I was here, as we increase the spin of the black hole and we move the inner edge of that disk closer in towards the black hole, we move the innermost stable circular orbit closer into the black hole, then we increase the amount of that line emission that is strongly gravitationally redshifted. So we kind of slump the line profile off to the redshifted part of the X-ray band. And we don't see, of course, just a single emission line in the spectrum. If you look at the spectrum, it's quite a complicated spectrum. It's got a big hump here. Where does that come from? That comes from the fact that this emission line is really just the sort of tip of the iceberg of a whole spectrum that gets emitted from the disk, which includes other emission lines, and it includes this Compton reflection hump. It's called the Compton hump. And so we take this whole spectrum and we relativistically smear it like this, and we end up with a spectrum like that. That fits these data extremely well, and we can use this effect here just to quantitatively read off the spin from these kind of data. And this shows you one particular analysis from that same data set. And what I want to highlight here is this is the spin, A star here, and that's the probability distribution we have for it. So we can say in this case that A star is constrained to be quite high, so higher than 0.9. So we can do this exercise now, and we've been doing that. We've been developing these tools for doing this over quite a few years, and collecting the data where we can do this for a large number of the supermassive black holes in galaxies, and sort of jump straight to a sort of plot of where we're at with this right now. This is about 32 objects plotted here. Of each one of these is one of these supermassive black holes. We can measure the mass of this through other techniques that I won't get into now, but sort of through more traditional techniques, we can measure the mass of the black hole. And through these kind of techniques I just described, looking at the X-ray spectrum, we can measure the black hole spin. And what we find is that a very large number of black holes are actually spinning very quickly. So a lot of black holes are spinning, almost right up to their maximum. Below something like about maybe this point here, or somewhere in the the 10 to the 7 to a couple times 10 to the 7 solar mass range. So this symbol here, M little dot, is a solar mass. So this is 1 million solar masses, 10 million solar masses, 100 million solar masses, 1 billion solar masses. Here, all black holes are rapidly spinning. As you go to more massive black holes, you start to get a number that are not rapidly spinning. And what does this mean? Well, we're starting to understand this in terms of how these things may actually form. And just to sort of briefly walk you through that, our current understanding of how galaxies form is that starting after the Big Bang, there were perturbations in the dark matter distribution, and then those perturbations start to grow through gravitational instability, and then gas falls into those dark matter clumps that are starting to form, and we get galaxies. In those galaxies, we start to get black hole. Well, in those galaxies, you start to get runaway collapse of massive gas clouds, and that's the first black holes that form. So there's now groups that are doing full-up computer simulations of this kind of process, and this is one of the cutting-edge simulations. They're called the illustrious simulation. In order to get galaxies right, in order to actually get galaxies that look like the galaxies we see today, they have to put what they call feedback prescriptions in, which means that in the middle of their growing galaxies, they need to include, for example, supernova explosions that will feed energy back into the surroundings when stars are formed. And they have to include the energy released by accretion onto black holes that gets pumped out. But through these kind of simulations, we can start to get a pretty good idea of how galaxies have formed, and the galaxies are the hosts for black holes, so we can start to get a good idea of how black holes grew. And in very recent work, this group has actually started to, each one of these galaxies has a little black hole in it. They've started to track what happens to the black hole spin. And interestingly, what they find is that, let me skip to this. Interestingly, what they find is that the paths that lead them to massive black holes, this is from one of their papers, didn't put reference up, this is Bustamante and Springle, the paths that give them massive black holes tend to give them low spin black holes. And that's because most of these massive black holes have formed through the merger of other massive black holes. And when you merge two black holes together, you tend to erase high spin. So you tend to get modest spin there. Down here, these black holes have been created by rapid accretion that goes on here. Okay, let's see. So how are we for time? So let's move on from these supermassive black holes to talking about stellar mass black holes. So these are black holes that form from the collapse of stars. And an important number of these objects we see in what we call black hole X-ray binaries. So if you have a black hole, a stellar mass black hole, it could be, say, 10 times the mass of the sun, and it's in a binary system with a normal star, quotes normal star, it can actually start to rip gas off that star and accrete that gas onto itself. And the result is a very, very powerful X-ray source. These are called black hole X-ray binaries. And one important thing here is that we can use accretion disk theory to tell us what the temperature of the accretion disk should be. And we find the maximum temperature of the disk, which is right down close in here, is firstly up in the millions of degrees, which means that it's in the X-ray band. So it's actually quite a convenient band to look at. And secondly, has a dependence on the innermost stable circular orbit, this R-ISCO. So again, as you make the spin high and you make this R-ISCO small, that will start to that will increase the temperature. So as you spin up a black hole, the temperature, the maximum temperature of the disk gets hotter, and so the predicted spectrum of this accretion disk, as you spin up a black hole from, I think the red line here is minus 0.9 up to the gray line. You make the disk hotter and hotter, and you take basically the black body-like spectrum of the disk and you shift it up. So again, you can go out with X-ray telescopes, you can measure the thermal spectrum of these kind of objects. This is data from an old object called Nova Musk, from a relatively new paper. And this is the X-ray data. You can fit a nice thermal spectrum, so a black body-like spectrum through it, and use the equation I just put up to start reading off what the ISCO should be and what the spin is. And in this particular object, you get spins of 0.6 or 0.7 or so. You can also, interestingly, do the same technique I just described for the active galaxies. You can do this reflection technique, this ion line broadening technique for these objects as well, for these black hole X-ray binaries. So that means it now gives you a chance to actually measure. This is a table of known spin measurements for these X-ray binaries, for a bunch of these X-ray binaries. And we can get measurements from this reflection modeling. This is the ion line broadening technique I discussed. And we can get measurements from CF is continuum fitting. It's this thermal black body modeling that I just described. And there's a few objects where we can do both techniques. And this is really important because it means that we can actually start to make sure we've got consistency here. We can do a sort of compare and contrast to make sure we've got consistency. And it's very encouraging that we actually do seem to have broadly consistency. Sometimes the error bars are quite big, so this just is a limit. But of course, it's consistent with this. But in many cases, but in all these cases, it actually is consistent. So that's giving us some confidence that we're measuring something. We're measuring the right thing. Okay, so in the last few minutes, I want to talk about the spin of binary black holes. And this is a new topic which has been made possible by the discovery of gravitational waves, which was awarded very quickly with the Nobel Prize. It's awarded with the 2017 Nobel Prize. So what is this about? Well, a binary black hole is, when I say binary black hole, I literally mean two black holes that are orbiting each other. And these can be, if they get close, they can be very powerful sources of gravitational waves. Gravitational waves are a very fundamental phenomena. It's ripples in the fabric of space-time. It's actually it's a wave-like mode within general relativity. So it's actually a ripple in the curvature of space-time that will carry energy and angular momentum away from the black hole and will make them eventually merge together. So this is the typical waveform that we expect for those gravitational waves. As the black holes merge together, as time goes on, they get closer and closer, so that they orbit each other faster and faster. And then right at the end, there's what we call a chirp. So they orbit each other very fast. The amplitude of the wave is very high, and then they merge and it dies away. And this was first seen in 2015 by the LIGO detector. So LIGO is an interferometer. It's got two pieces. One is in Louisiana, so it's in Livingston, Louisiana, and then the other one is in Washington State. So it's the west coast of the US, which is about 3,000 miles from this spot. And these two detectors act as one. And to really have a confirmed event, you want to see the gravitational wave signal in both detectors. So this is the detector. This was the first detection of one of these binary black holes. This is the detection in Hanford. This detection in Livingston. So what do we, how can we measure the spin here? Let me just move through to here. Well, there's as the black hole is rotating around, as it's sending out these gravitational waves, you can think that if the black holes have spin to them, so suppose they've got some spin around an axis that I'm sort of highlighting with the pointer, then that will, again, induce a tornado-like motion of the space. And the other black hole will kind of pick up a bit of an extra sense of rotation around the black hole due to that. So the orbit of the black hole will be a little bit faster. The period of the binary will be a little bit faster than it normally would have been, if there's a spin of the black hole that's strongly aligned with the angular momentum. So if the black hole is having a aligned spin, that will give us this. So what that will mean is that if you sort of stare at this formula, what this is saying is if you have the spins of the black holes, A1 and A2, and we dot them with the unit vector that's pointing in the direction of the angular momentum of the binary itself, so we're just looking at aligned components, that gives us something called the effective spin. And we weight it with masses. That gives us something called chi effective, which is the effective spin. That effective spin is going to change the phasing of these peaks. And that is something that LIGO and other gravitational wave detectors are actually very sensitive to. So we can actually look at the data and try and pull out this kind of effect. And it's been seen. So this was one of the first detections of it from the LIGO team. This was for a particular gravitational wave event, GW 151226. And the thing to look at here is this axis. This is the probability distribution of this chi effective. And you can see that it excludes zero. So it's got a non-zero probability of a finite chi effective. So this is a positive detection of some spin physics in this gravitational wave detector. And you can do this for the other events, and this is already slightly out of date because now LIGO has announced a large number of events just very recently. But the important thing here is that compared to what I was just telling you about from the X-ray measurements, these are all pretty small effective spins. So zero is here, and most of these gravitational wave events are actually consistent with zero. There's a couple which have tails out to quite high spins, but most of them are consistent with zero. And a particularly interesting event, I sort of put up the paper here, is that this was announced. I mean, looking at these dates, this is all really recent stuff. So this was in just this year. There's this source GW 190814. And there's many interesting aspects of this source. One is that it was the merger of a 23 solar mass black hole with a 2.6 solar mass object. So this 2.6 solar mass object is either the most massive neutron star we know or the least massive black hole we know. We don't know which yet, but it's one of those. Now, if you read past the 1,000 authors plus all their affiliations, and I think on page 4, you finally get to the abstract. Another interesting aspect of the abstract, if you look at here, is that the dimensionless spin of the primary black hole is constrained to be less than 0.07. So there's a very tight constraint on this spin, on this black hole, to be almost non-spinning at all. So broadly, when you look at the set of gravitational wave results, I mean, it's growing all the time. This is from the latest their latest press release. They now have something in excess of 50 or so events that are detected. And here, this nice graphic shows the mergers. So this object and this object merged to give you this object. But the vast majority of the objects that are detected by gravitational waves are spinning very slowly. Whereas the vast majority of objects that are detected by the so-called electromagnetic black holes, these are the X-ray astronomy black holes, are rotating very quickly. So there's something interesting here. So this is telling you that there must be a diversity of formation channels for black holes. The black holes in X-ray binaries are generally rapidly spinning. And we believe that they must have actually, at least in most cases, they must have been born that way. It's actually hard to come up with scenarios whereby the black hole in the X-ray binary can be spun up by accretion. There's usually not enough matter around to do that. By contrast, the black holes in black hole binaries, which we see through gravitational waves, a few of them have some detectable spin. One or two of them may even be spinning quite quickly, but the majority of them seem to be spinning very slowly, and at least one case is extremely slow. It's less than 0.08. So we're clearly dealing here with different populations of black holes, and we're still struggling to understand exactly what this is telling us about how black holes grew and formed. One idea is we've got binary massive stars. So we have two massive stars. I mean, this shows them joined. They don't quite have to be joined, but two massive stars. One of them can go supernova. That gives us the X-ray binary black hole. Black hole and the normal star. Then maybe the other one goes supernova, and it gives us a binary black hole. However, this is strange because in this scenario, we know that this black hole must be rapidly spinning from the X-ray astronomy, but somehow by the time we get here, most of these sort of objects are slowly spinning. Another route is that black holes are formed through another route to the binary black holes, is that black holes form from single stellar evolution. So we get a single massive star all by itself. It forms a black hole, but this happens in the middle of star clusters. And basically the black holes that are formed sink to the middle of the cluster. They start to find each other, they pair off, and that's how you form binary black holes. And then there are much more exotic ideas, black holes that formed in the early universe that are now forming these binary black holes, and etc. So it's still very, very much an active field. So to move to my conclusions, spin's a very important quantity of black holes. It's a fundamental property of black holes. It's a fossil remnants of how they were formed, and it's a very potent energy source. So it's an important quantity to look at. We now have multiple techniques for measuring spins. So with using X-ray astronomy, and we've got a couple of techniques just within the X-ray astronomy world, looking at disk reflection and the thermal spectrum. And as in recent years, we now have gravitational waves we can use to probe spin. And the current results are interesting. Many supermassive black holes are rapidly spinning, but there is a population of modest spin holes appearing at high masses. And this actually fits in pretty well with our ideas of how supermassive black holes grew and were formed in the first place. On the other hand, in the low mass black holes, in the stellar mass black holes, it's much more puzzling. We know that black holes in X-ray binaries are mostly rapidly rotating, but the similar mass black holes in the binaries, the ones we see through gravitational waves, are slowly spinning. So there must be some diversity of ways that the black holes can form. And that's one of the areas that's still very much cutting edge research, trying to understand that. So I will bring it to a close there and take any remaining questions.
Thank you very much, Chris. That's really interesting to see some of the bleeding edge research, I suppose. I'm going to read out the questions in the order that they came in. I'm not really going to distinguish between YouTube and timeout. So first one from Havoc Wave. If the spin parameter A is 0, is it possible for a black hole to not have a spin? What happens in this case?
Excuse me. In a formal sense, that is possible. It's for me if you can have a a black hole that has no spin at all. So there's no frame dragging effects. There's none of these effects at all. It's perfectly well behaved. It's all the equations I had, you could have A in and just set A to 0. Of course, it's a bit of a singular case in the sense that no black hole in practice will ever have strictly zero spin. And any black hole will have a tiny bit of angular momentum. They're classical objects, let's face it, so they'll have a tiny bit of angular momentum. And there'll be some tiny spin parameter. But yeah, you can mathematically, in fact, the very first solutions discovered, this Schwarzschild solution, is the solution for a non-rotating black hole.
Thank you. Our next question from Andromeda. How can a photon escape a circular orbit for us to see it?
It's a good question. So the circular orbit for a photon is not stable. And so you can almost think of it a little bit like a sort of storage ring. If you have some source of emission that's putting photons into circular orbit, they'll typically do a few orbits and then they'll escape. So if you actually look very carefully at, let's see if I can take it back there. I don't know if this was carefully enough done, but if you look carefully at this, you can see there's actually several rings in here, And this corresponds to photons that have done one orbit and then escaped, and then those that have done two orbits and escaped, and those that have done three orbits and escaped. That's your whole sort of set of rings in there. But yeah, they can escape because fundamentally it's an unstable orbit.
Okay, great. Two questions, this time from Ursula Shaw. First question: if all photons within the photon circular orbit accrete into the black hole, or onto the black hole, excuse me, how can we image within this region? I.e., what is the difference between the photon circular orbit and the event horizon?
That is a good question. So if you had, because this is often this is something that's often talked about for the EHT image. So if, for example, you had a black hole and it was in front of a screen of light, you had some screen that was entirely in the background, then in fact the photon circular orbit essentially becomes the image of the event horizon sort of fills up to it, in the sense that that sort of becomes the bounding edge for where photons from the background either fall into the black hole to start with, or don't. In this case, however, it's not quite the case that there's a background screen. There is actually an accretion disk here. There is matter that is actually inside the photon circular orbit. There is matter in there. And if it sends its light out, not on circular orbits, but it sends its light out on more like radial orbits, that light can still get to us. So light can still escape as long as it gets sent out in sort of a fairly radial direction, anywhere outside of the event horizon. And if that material is genuinely close into the black hole, it will actually appear to be inside the photon circular orbit image. That's a good question. It's a subtle issue.
Great. And second question, also from Ursula. Also, is the Roche limit applicable for black holes? Is it as well defined as the innermost stable circular orbit?
The Roche limit. So let's see. So this would be for a black another object coming close to the black hole, maybe. So normally when we think of the Roche limit, we think of it's the place where if you brought something close to it, it would be disrupted. And there is such a well-defined limit for black holes, but it's a function of what you're bringing up to it. So, for example, if you have a star that you bring that orbits close to a black hole, if it orbits too closely, it can be ripped up by the tidal forces of the black hole. There isn't so much a completely well-defined radius, not in the same sense that these special radii are, because it depends upon the density of the object you bring up. The denser the object you bring up, the closer you can bring it before it gets disrupted. But yeah, I mean, these kind of concepts like Roche limit, they actually do apply for black holes too.
That's great. This one from Kang. How is the inverse Compton's effect changed at the border max spin and min spin? I hope I copied that down right.
So I'm not quite sure I understand the question. Let's see. What do you mean by the inverse Compton effect?
Yes. Where was... yes, it's in the timeout chat.
Okay. Yes, no, I'm sorry, I don't quite understand that question. Maybe they're referring to the Compton reflection hump here. So what this is basically, if you have, sorry, let me come back to my accretion disk here. If you're thinking about how X-rays reflect off this disk, then if you have a very high if you have a very high energy, absorption lines or absorption edges in the disk, then it'll tend to just get Compton scattered. So it'll come in, the photon will come in, it'll Compton scatter off one of the electrons in the disk, and then typically be scattered out. And that's what this red hump is here. That these are Compton scattered photons. So inside of here, the photons tend to be absorbed. And so, like anything, this Compton scattered hump is redshifted. It's like everything else, it gets redshifted. So, as you go to more rapidly spinning black holes, to say spin of one, then you'll tend to bring that redshift in. So, I think that may be what the question was asking about.
Okay.
Sorry if I messed that up. Yeah.
Okay. We have something like 15-ish questions to go.
Okay.
So I'm going to try and work through them as quickly as we can. I don't imagine you'll be. I mean, how long can you stay for?
I've got another 10 minutes or so. So
okay.
I'll try to answer them as efficiently as I can. Yeah.
Sure. From DSID on YouTube, say you have a black hole spinning clockwise and one counterclockwise with their accretion disks following their black hole spin. When those two merge, could they send all this matter out into space, since the spin after the merge won't be the same?
That's a good question. So, so that you've got black holes spinning in opposite directions, and let's go to say this. So you've got black holes spinning in opposite directions, and they've each got their accretion disk with them. So what would happen quite as the black holes got close to each other, the accretion disk would inevitably be disrupted, because the tidal forces of each black hole would just shred the accretion disk of the other black hole. And so by the time they actually merge, there might not be that much left of the accretion disk itself. There might be general gas around that's been kind of blown off, but there may not be very much of the accretion disk itself. Now, what happens to that is actually a really interesting question. I did a research project on this quite a few years ago when we started to think about these merging black holes, and it is actually possible to get some pretty fast ejection of material as the two black holes merge together. There's a lot of energy released. I mean, that's an understatement. There's a lot of energy released as the two black holes merge together, and if you do have gas or plasma in the environment, then that can actually get shot out at borderline relativistic speeds.
Okay, just so Ailman YYY on YouTube. I can't see your question. If you could repost that in the YouTube chat, that would be great. I can't see it scrolling down. If I've missed it, my mistake. Moving on from the list I do have, from Janos Takatsky. From the theoretical point of view, is it possible to have a naked singularity? Can you tell me why it is not realized in nature? Is there a dynamical reason behind that?
Good question. Very good question. So if we come to, let me come to my diagram of the special radii. So here's the special radii. This is the event horizon. Now, mathematically, what happens if you were to write down the mathematical solution for a spin parameter greater than 1 is you'd end up with a singularity without an event horizon. So that would be a naked singularity. Now, there's fundamental problems with that. I mean, you can think of it for a start as thermodynamic problems, in that gives you a uncontrolled inflow of information, if you like, into the universe, which we don't really like. What I would say is we can't prove, however, that this is impossible. I mean, there's no theorem that says you can't do this. We sort of botched this up by saying that there's something called the cosmic censorship hypothesis. We hypothesize that we're not allowed to do it, but there's no theorem that says we can't do it. Two more comments on that. One is that what we can show, what we can write down a theorem for, is that if we start off with a black hole that's that's spinning with a spin less than 1, and there's no sort of normal process we can do. There's no sort of, we can't force feed the black hole high angular momentum material and make it go higher than 1. That you'd have to feed it, some exotic material to do that. And then the second thing is that there are actually some really quite interesting papers out there that show that you can actually have solutions with a greater than 1, where you mathematically replace the singularity with some string theory motivated structures, and you can actually show that's a consistent solution. So one interesting idea is there may be things out there that look like black holes that are spinning greater than 1, called super spinners, which in GR would be naked singularities, but it's possible to have extensions of GR with some string theory motivated ideas to basically remove singularity.
Okay. On YouTube, which I think you've already answered this question, NeoSoin says, is there any difference in the gravitational waves of the black holes if the black holes have opposite spin?
Yes, I mean the precise waveform will be different because the frame dragging will be different, but broadly the waveform will be the same, and we'd be able to measure that there's opposite spins there. Yeah.
Okay. Ailman YYY's question, which I don't know whether this fits in chronologically, so I'll just stick it in here. If we tap into the black hole's energy and using if we tap into the black hole's energy and by using magnetic coils extract that energy, how I understand it, will the black hole eventually lose its spin energy?
Yep, that's right. We'll slow it down, and in principle, we can slow it down all the way to 0, and we can extract all of its spin energy. This is actually sort of a set of theorems that Roger Penrose put in place about how you can do this.
Okay. Jim Slight on YouTube asked, did you intimate that the supermassive black holes and galaxy formed at the same time?
Yes. So, I mean, we don't know for sure. This is one of the big questions out there, exactly how and when the supermassive black holes formed. There's some kind of co-evolution or codependency that goes on, because we see that black holes shape the way that galaxies form, and galaxies must in some sense shape the way black holes form, because that's the source of the material that forms them. So there's some codependency there. We see that black holes are in place very early on in the universe's history. I mean, we see quasars at some very, very early times. So we know black holes, at least some black holes, must be there very shortly after galaxy formations happened. But this precise codependency and coevolution between black holes and galaxies is very much an interesting question for research.
Excellent. Just to update you on about 11 questions.
Okay.
From RP on YouTube, where does the angular momentum in the universe come from? Which I suppose is a bit broader than the scope of this talk, but...
Oh, yes. Good question. That one's a bit above my pay grade. There's a very interesting literature on something called Mark's principle, which basically says that, ask the question, what defines the non-rotating reference frame? Something is telling us what the non-rotating reference frame is, and Mark's principle says it's the large-scale structure of the universe, basically. So by definition, the overall universe has no angular momentum. I'm not an expert at all in that area, but I refer you to the literature on Mark's principle.
Okay, from on YouTube, Badinga Namcha. In the process of a binary black hole, I'm going to assume that's collision or similar. Let's say that both the black holes the same gravitational force and spin momentum. I see. I'm not quite sure how to interpret that. I'll just read it out literally.
Sure.
In the process of a binary black hole, I assume collision or orbit. Let's say that both the black holes have the same gravitational force and spin momentum. Do they keep revolving on their own like they used to?
So I think probably, when you have let me go to, there's a cartoon that Kip Thorne did, which is quite nice. So you have your two black holes that are spinning away, and then of course what happens is they come together, they merge, and then you end up with one final black hole that's being produced. And the final black hole has spin associated with it. The spin of this black hole is a combination of the spins of the black holes that came together, plus some component of the orbital angular momentum. So it's actually a somewhat complicated mix that goes into the spin of the final black hole, because not just the spins of the individual black holes, but that's what's left at the end. It's this.
Thank you very much. From David Tristini, could one also think of a process for small spinning black holes to merge and statistically have opposite spin to yield non-rotating black holes? Could there be a process where opposite spin black holes attract more?
Attract more. So yeah. So I guess this is in the sense of how can you produce slowly spinning black holes, maybe. So again, sort of reference to this cartoon, it's interesting to think about the spin of this final black hole. I say it comes from both the spins of the spins of the initial black holes, but also the angular momentum of the black hole. So if you start off with non-spinning black holes and you bring them together, you actually end up with a black hole that is spinning at something like about 0.6 or 0.7 in terms of A. To nullify that spin is actually kind of hard, and there's been some work to try to come up with evolutionary paths that can give you a very slow spin here. It's a bit tricky to do actually through these kind of mergers.
Thank you. Next question from Paulo Rodriguez Hidalgo on Hidalgo. It's been years since I've done Spanish. Fantastic talk. Is there any study on whether there is a relationship between spin and outflows coming from the accretion disk?
Yeah, what a good question. Yes, I mean that's the kind of thing that goes on a lot in my group and sort of colleagues of mine. A lot of the AGN where we can actually see the outflows best are all spinning very fast. But there are a few that are spinning more slowly, and we sort of try to look at what the differences are in the outflows. So there's no actual strong conclusions yet, but this is a good question that we're trying to look at.
Okay, we have another question from Dinga. I'm one of them. Change this rotation so it can merge with the others. Merge together. I'm not really sure what's going on there. He's retracted a message and then posted that. So, Badinga, if you could repost that in YouTube chat, that would be great. I can't really intuit that. Very sorry.
Will, perhaps we've had quite a few questions, and if you said you only had 10 minutes, Chris, then I think we've reached that.
Okay, sure. Yeah.
I'm sorry to interrupt, but
yes.
But
shall we do what ones we have left? I'm just going to see if we've got any particularly interesting questions, and then hopefully do those quickly. So, say 3 questions.
Sure. Yeah. So take 3 more, and then we can call it a night.
Just because we need to stop somewhere. So.
You've gone quiet, Will.
Sorry, no, I had myself on mute. I'm reading through the questions. There's one question asking whether this is a strictly classical. There's one question where Laios is asking whether spin is a strictly classical angular momentum, which I believe it is.
In this case,
from Sebastian Lung on YouTube. This is somewhat interesting. When two black holes merge, don't they lower total volume? Does that mean a lot of it is released? Why didn't the early universe, before expanding enough, create a singular massive black hole?
Sorry, say it again. When two black holes.
So when two black holes merge, don't they have a total lower volume, i.e. you have a greater mass black hole that's going to not proportionally increase the size of the event horizon? Does that mean a lot of it is released? So basically your mass to volume ratio, I think he's talking about, is going down, or volume to mass, whichever it is. Why didn't the early universe, before expanding enough, create a singular massive black hole?
Yeah, so when so I won't really address the early universe that much, because that's a rather different setting, and that's not really what my expertise. In terms of the energy released in merging black holes, it's in principle there could actually be a lot of energy released. In practice, it's something like a few percent of the rest mass energy is released. And it's released very quickly. It's released over a few light crossing times of the black hole. So the actual luminosities, the gravitational wave energy outputs per unit time, are colossal. I mean, some of the brightest, most powerful things in the universe. But it's in gravitational waves, so it barely couples to anything. So it doesn't actually do much damage to anything. But yeah, the energy release is colossal.
Great. Two more questions. So from Ursula Shaw again. Why does the slow spin and fast spin dichotomy of the data indicate two distinct populations of black holes? Does their correlation with detection methods not suggest detection bias instead?
Well, that is a good, yeah, that's a very good question. Detection bias, and this is something we've thought long and hard about. So you tend to be biased to see rapidly spinning black holes, in the sense that those are the ones that are more energetic. The spin effects generally show themselves quite well. So when we see the high spin black holes in the X-ray techniques, we have to ask ourselves very carefully whether we're being biased. We don't think we are. In the case of the X-ray binaries we see in our galaxy, because essentially we have what astronomers would call a volume limited sample. We basically see every black hole X-ray binary that's gone into outburst in our galaxy, period. So we see pretty much a representative sample of all the black hole binaries in our galaxy. And then for the gravitational waves, the fact that it would be easier to see the high spinning below spin. And in fact, that's kind of what this plot was showing. I didn't actually go into details here, but this was there's two probability diagrams here for the spins. The solid one, this is for each object. The solid one is actually from the standard LIGO analysis, and then the unfilled one is a reanalysis of the probability histogram once you account for selection biases and other things. And you can see that it systematically shifts the probability distribution down to lower spins, because it would actually have been easier to see high spins. So you're absolutely right. I think it was Ursula who asked the question. Absolutely right that you have to worry about selection biases a lot. But we think in this particular situation that the dichotomy stands, even given the selection biases.
Okay, thank you very much. I think we'll probably call that last question, because you've kind of got to get on with your thing. You've kind of got to get on, and wouldn't be fair to keep you here too very much longer. So thank you, Chris, for the talk. Thank you, everyone, for coming to watch and asking questions. Very active audience today, which is always good to see. I hope you all have a nice evening, or, well, not necessarily evening, I suppose. We've got people from all over. We've got at least 2 people from Greece in the chat, someone from Portugal as well. All very nice.